Today's lecture is about the wave analyzers. The presentation scheme will include the introduction to wave analyzers, their principle of operation, the types of wave analyzers, basically the frequency selective wave analyzer and the heterodyne type wave analyzer, and finally we will be discussing the applications of these wave analyzers. Now, what we say that a complex waveform is said to be composed of a number of frequencies, and each of these frequency components have a different amplitude, their different phases and obviously the different frequencies. So, in many of these applications we require to analyze these frequency components regarding the measurement of their amplitude, their frequency, their phase, and this type of analysis is known as the wave analysis. And the circuits which are used for analyzing such type of complex waves are called the wave analyzers. Now, what we do is that basically we need to filter out the different frequency components one by one, and after filtering or after tuning the frequencies one by one, we will measure their amplitude and their phase. These wave analyzers, they basically measures the amplitude, and the analysis of a waveform means the determination of, as said earlier, the determination of the values of amplitude, frequency and sometimes the phase of these frequency components. A wave analyzer is an instrument which is designed to measure the relative amplitude of the single frequency component in a complex waveform. They basically act as a frequency selective voltmeters, since they are measuring the amplitude. So, we say that they are basically the voltmeters, and simultaneously they are the frequency selectors also, because we are going to tune the frequencies one by one and then we will measure their amplitude. And now, the networks of these types of narrow band of frequencies, they provide a high degree attenuation to all other frequencies. Here we will be selecting one of the frequencies, while at the same time there should be a high attenuation to the adjacent or to the other frequencies. So, the wave analyzers, the tuners available in the wave analyzers, they are of a particular bandwidth, so as to select one of the frequencies and reject simultaneously all the other frequencies which are not under the consideration at this moment. Now, as we are discussing that the complex waveforms, they comprises of a number of frequency components. For example, if we talk about a pulse is said to be composed of infinite number of sine wave frequencies, and these frequencies, they can be evaluated as the fundamental frequency, which is equal to the frequency of the pulse and its harmonics. The frequency equal to the pulse will be the fundamental frequency, and the harmonics will be their multiples of the fundamental frequency. In case of the pulse, we say that larger the number of frequency components in a pulse, more ideal will be the pulse. So, it is very essential to determine the frequency components of a pulse in order to make it more and more idealistic. In infinite number of frequency components, it constitutes an ideal pulse, or otherwise if the number of frequency components in a pulse, they are low, then their the errors such as the sag or the overshoot or the undershoot, these types of errors occur in the pulse. So, what we are talking of is that any type of complex waveform, it comprises of a number of frequency components, and we need to filter those frequency components, and we need to determine the amplitude of these frequency components. Now, we use the waveform analyzers for such type of analysis. Now, there are manual analyzers and there are automatic wave analyzers. Like instruments which require the user to make the manual search, Manual search means tuning the frequency one by one. We are going to vary the value of either R or C of the filter, and then we are going to tune one of the frequencies and will measure its RMS value. Then again we are going to vary the values of R and C, and then we will measure its RMS value. So, this is the manual search. So, one by one we allow the frequency component to pass through the filter circuit by manually adjusting the tuning frequency, and these types of circuits, they are the manual wave analyzers, where everything, the tuning of the frequency is done manually, while those which perform the frequency sweep automatically. There are some waveform analyzers which automatically sweeps the signal and show the complete amplitude frequency response variation. Frequency response means here we are talking of the variation of the amplitude with the different frequency components. They are displayed on the display screens, and such type of automatic wave analyzers having the visual displays are called the spectrum analyzers. They very much, if we see that they also have a display screen, and the CROs also have a display screens. Now, if we want to differentiate between those two instruments, then the spectrum analyzer, it gives the different amplitudes of the frequency components, means it is the variation of the amplitude or the voltage with the frequency. So, spectrum analyzers, they display the variation in the variation of the amplitude in the frequency domain, while in case of CROs, the variation is with respect to the time domain. It is with time, the variation of the signal, how it is varying with time is displayed in the CRO, while in case of the spectrum analyzers, the variation is in the frequency domain. So, that is how the spectrum analyzers, they differ from the CROs. Now, coming on to the principle of operation, the block diagram shows the principle. The band pass filter, here it is used to select one of the frequency components from the cluster of the different frequencies. Now, selecting one of the frequencies is called the frequency tuning. Now, the band pass filter, it plays a very important role, since it will determine the resolution of the instrument, because as said earlier, the filter should be such that it should be able to tune only a single frequency and should be able to remove all the unwanted frequencies, or which is not the frequency of interest. The selected or the tuned frequency is then fed to the preamplifier or the amplifier stage, and its amplitude or the RMS value, the root mean square value, is indicated by the output meter or the display device, whatever it is. Now, by changing the tuning frequency of the band pass filter, we can select the frequency components one by one, and simultaneously we can measure their amplitude and their phase also. Right now, we will be dealing with the measurement of the amplitude or the RMS value. Now, coming on to the type of wave analyzers. The wave analyzers are divided into two groups depending on the frequency ranges that are used over here. The frequency selective wave analyzer and the heterodyne type wave analyzers. Both are operatable in the different frequency ranges, and this is the basis of the classification of these two types of wave analyzers. Now, this shows the block diagram of the frequency selective wave analyzer. The signal, the input signal which is to be analyzed, which is having a cluster of number of frequency components, it is first of all fed to the input attenuator. The signal is attenuated, we can decide the range of the input signal. The input attenuator, it suppresses the signal in case if the amplitude of the input signal is going beyond the range, or we can say that the input attenuator, it basically it is a range multiplier. Now, this attenuated signal is then amplified by the driver amplifier, which is basically used for maximum power transfer. It does not amplify the voltage, it is just the maximum power transfer. It has been used for just transferring the maximum power, or we can say it is a pre-amplifier, and the output of this driver amplifier is fed to the most important component of the wave analyzer, which is the filter of high Q. The figure shows this high Q filter circuit, in which we have used the RC components. These RC components, the value of the frequency that will be filtered out or that will be tuned by this frequency selective wave analyzer, it depends upon the value of RC. The value of RC, it is basically shown over here, it is a second order filter which is based on the operational amplifiers, and we will filter out one of the frequencies. This selected frequency, manually selected frequency I mean, this manually selected frequency is then fed to the meter range attenuator and the output amplifier. Now, the output signal from this output amplifier is then it can be directly fed to the output meter, which can directly measure the amplitude or the RMS value, or it can be simultaneously fed to the output buffer amplifier, whose output can be fed to maybe an electronic recorder or the electronic displays, whatever it is. So, this is how the frequency selective waveform analyzer works. This wave analyzer is basically employed in the audio range of 20 hertz to 20 kilohertz. The filter, as said earlier, is the most important component of this analyzer, of this type of analyzer. It consists of a cascaded arrangement of RC resonant sections and filter amplifiers. Now, the most important thing is about the capacitors and the resistances that have been used in this filter circuit. We generally use the close tolerance polystyrene capacitors, since they show very high accuracy, and simultaneously high precision potentiometer are used for tuning the filter to any desired frequency within the selection pass band. So, both these components, the resistances and the capacitors, they should be of very high tolerance and tolerance regarding the capacitors, and they should be highly precise considering in reference to the resistances. The final amplifier stage, as suggested earlier, it supplies the selected signal to the meter circuit and to a buffering amplifier, and the buffer amplifier can be used to drive a recorder or an electronic counter, as stated. Coming on to the next type of heterodyne type of wave analyzer, the figure shows the block diagram of the heterodyne type of wave analyzer. Now, first of all, what does heterodyning means? Heterodyning means the mixing of two frequencies through a mixer circuit such that the output is equal to the difference of the two frequencies. So, heterodyning means basically the beating of two frequencies through a mixer circuit, and that is what we will be doing in this heterodyne type of wave analyzer. Well, the input signal which is to be analyzed is fed to the attenuator. Again, it is a range multiplier. In case if the peaks of the input signal are beyond the range, then we can attenuate them, rather in other words we can increase the range of the input signal which can be analyzed. Now, the output of this attenuator, it is required in this analyzer, the attenuator provides the required input signal for heterodyning in the first mixer stage. The frequency generated by the local oscillator is basically from 30 to 48 megahertz. the frequency of this local oscillator can be set using the frequency range switch. Now, the local oscillator frequency and the input frequency is fed to the first mixer, which mixes both the frequencies from the local oscillator. Let the frequency generated by the local oscillator be F L and the frequency of the input signal be F I. Then the mixer produces an output which is F L minus F I. It is always considered that the local oscillator frequency is always kept higher than the input frequency, and the output of the mixer circuit is known as the intermediate frequency, which is currently in the heterodyne type of wave analyzers. It is capped at 30 megahertz. So, in order to obtain an intermediate frequency of 30 megahertz, the local oscillator frequency should be always 30 megahertz higher than the input signal frequency. For this purpose, the capacitor used in the oscillator and the capacitor which is used for tuning, they both are ganged, such that they both are the ganged capacitors, such that the input signal frequency is always 30 megahertz higher than the input frequency, that the local oscillator frequency is 30 megahertz higher than the input frequency. The output of the first mixer, which is the intermediate frequency IF, it is then fed to the IF amplifier. Now, here we are not choosing a particular frequency. The whole band of the input signal is currently being passed through the first mixer, such that it is being subtracted from the local oscillator frequency. This has been done just to bring the band of the input signal, the frequency range of the input signal within the desired range, and it is then fed to the IF amplifier. The output of the IF amplifier is then fed to the second mixer. Now, again this whole band of frequency of the input signal is, the filtering has not been done as yet. The output of the IF amplifier is now fed to the second mixer for filtering. Again there is a local oscillator, this time we are using a crystal oscillator which is of 30 megahertz. Now, since the second mixer, it mixes the output of the IF amplifier and the frequency generated by the crystal oscillator. Now, here it has been set such that it has been centered at the 0 frequency. The output of the difference of the two frequencies is such that it is 0. In other words, we say that the output of the second mixer is rectified and it is then fed to the active filter. Now, this filter, this passes the signal and is then finally it is displayed on the meter, which is calibrated in terms of volts or in decibels. Now, again coming to this, the first mixer stage produces an output which is the difference of the local oscillator frequency and the input signal, which produces an IF, and this IF, as said earlier, it is the whole band of frequencies. It should not be mistaken that it is a single frequency, it is the whole band of frequency, and it is then filtered in the second mixer, which produces the rectified output for a particular frequency as set by the mixing of the input signal frequency and the crystal oscillator frequency at the second mixer stage, and the selected component is then passed to the meter amplifier and the detector circuit through an active filter having a controlled bandwidth. Now, coming on to the applications of the wave analyzers. The wave analyzers have a very important applications in the field of the electrical measurements, the sound measurements, the vibration measurements. Now, the wave analyzers are used industrially to detect and reduce the sound and vibrations generated by the rotating electrical machinery and equipments. Now, in case of the industries where there is large amount of noise which is generated due to the movement of the motors or other rotating equipments. Now, what we do is that we feed these noise into the wave analyzers and then determine their frequency components, and we try to suppress these frequency components by some or the other techniques. So, these wave analyzers, they play a very important role in reducing the sound effects and the vibration effects that are generated by these equipments. So, in this lecture we have discussed the waveform analyzers, the importance of waveform analyzers, and where do we use these waveform analyzers. They are used for selecting the one of the frequency components from the cluster of the complex waveforms, different cluster of frequencies. We will select one of the frequency, and as said in the principle of operation, that this selected frequency is then measured by the meter, and we have to use some pre-amplifiers and amplifiers, and in order to have the maximum power transfer to the load. And then we discussed about the different types of wave analyzers. In our scope, it was the frequency selective wave analyzers and the heterodyne type of wave analyzers. In the frequency selective wave analyzers, we had a high Q filter circuit through which we can filter out the frequencies one by one, and then these filtered frequency, as said earlier, it can be measured by the meter, or it can be displayed onto electronic recorder or any display screen using the output buffer circuit. And after that, we discussed the heterodyne type of wave analyzer, which is totally based on a different concept of generating intermediate frequency or the IF signal, which is produced by mixing the local oscillator frequency and the input frequency, and that is another way of selecting one of the frequencies. And now, after selecting the frequency, the theory remains the same, that the selected frequency is then measured in regarding the terms of the voltage, etc., or the RMS value. And finally, after that we discussed the various applications of these wave analyzers, like we discussed it in the industries where large amount of noise or vibrations are there. So, we can damp those noise or these vibrations by analyzing the frequency components in these unwanted signals or unwanted vibrations. And that is all for today, and hope you might have enjoyed the lecture. Thank you.